Hello, I'm Andy Briggs, and welcome to the amazing Astronomical Alphabet, a weekly programme in which my Astro Radio co-presenter Daz and I will be talking about anything astronomy related which begins with the week's letter of the alphabet. We'll each choose some things to talk about which are in some way related to the universe, but neither of us will know what the other has chosen. We will then reveal facts about them which are weird, strange, bizarre, or simply interesting. Well, welcome back, listeners, to the amazing Astronomical Alphabet with me, Andy, and my esteemed co-presenter here, Daz. How are you, Daz?
I'm fine, thank you, Andy. It's a little bit cooler here now. We're just waiting for a storm to roll in, so it's going to be fun and games later. But at least hopefully it'll clear the air, and we'll be able to, I was going to say get back to some sort of normality, because we've had our summer, we've had our week. So
right.
Yeah. So
well, we've still got probably another 2 months of our summer left. So.
Yeah. Well, I'm coming over to the Canaries. Hopefully, fingers crossed. In when are we coming? October, I think I am. Oh, no,
are you?
No, September. So yeah.
Whereabouts?
So we're going to. I think this time it's Lanzarote. We're doing.
Oh, nice.
And then in December we're doing Vera Ventura. So
oh, lovely.
Yeah, hopefully. Well, we booked 2 just in case, and we might just slip one in between. I don't know.
You must come and see us at some point, Daz.
We'll do. I was actually looking at coming over for your eclipse.
Yes.
But when I looked at it, it's, as you said, it's southern Spain, isn't it? And it's late in the evening, isn't it?
Yes, that's right.
Yeah,
that's right.
So, but then I looked. I thought, well, what will it be if I stay at home? And we'll get 92% anyway. So,
right,
92% coverage. So
that's
we'll see. We'll see how we get on.
Yeah.
So, I no doubt the hotels are all filling up over there already for it. So
yeah, I'm sure.
Yeah.
So, the amazing Astronomical Alphabet, we have reached the dizzy heights of the letter H this week. Yeah. So I think it's your turn to go first, Daz. So off you jolly well go.
H is for hippopotamus. No, seriously. H is for hydrogen.
Hydrogen.
I thought we'd start with a sort of like a little quick one to get us rolling. As we know, after the Big Bang and all the primordial soup settled down and cooled down, and atoms were beginning to form, we ended up with a universe that was basically just full of 75% hydrogen, 24% helium, and I think the other one was 1% lithium or something like that.
Right. Yes.
And of course, we know hydrogen basically is the building blocks of everything since then. It powers our suns through nuclear fusion of hydrogen. And as it goes through its process, it creates all the other elements. While it's burning its hydrogen, it's what we call the main sequence part of the Herschel-Russell diagram, and it's did I say Herschel?
Yes, you did.
Hertz.
I think it's Hertzsprung.
I've just given away one of my.
Is it William Herschel by any chance?
No, it's not actually.
Right, okay.
But oh dear me. Go on, get a grip. Yeah. So the Hertzsprung-Russell diagram. It will sit in the main sequence while it's happily burning hydrogen, turning hydrogen into helium. But then what I was really going to talk about is what happens once the hydrogen starts to run out. And what will happen with our star is it will then start to move off the main sequence towards the red giant stage, which means in the diagram, whereas the main sequence goes left to right diagonally, it will move up to the right top corner where all the big red supergiants are living. But to actually get there, it has to go through. What happens is all the hydrogen in the core is used up, and it starts to contract, causing, and of course we've got you've got to have this this balance of gravity and outward pressure, which we may talk about later. And what happens is it causes more heat in the core as it starts to shrink down, and as the heat grows, the hydrogen then the hydrogen that sits around the actual core in a thin shell starts to fuse again,
Right.
and this is called hydrogen shell burning. So this isn't actually hydrogen burning in the core. This is actually burning outside the core.
Right.
And this has a couple of effects. Is that it makes the star actually expand, so it becomes more luminous, so it becomes brighter, but it gets cooler. And so as it moves up towards, as like I said, the red giant stage, you've then got, as I said, you've got the hydrogen burning in this shell around the actual core, where so it's producing helium, which is then being dumped back into the core. And as as more and more helium gets into the core, it increases more and more pressure, which again causes a bit more expansion. So again, the star is getting that much bigger. And eventually the temperatures and the pressures get so high that the helium overcomes its urge to be not the opposite to attracted, to be rejected by all the other helium, atoms, and they start to fuse together, and then we get what they call a helium flash, which then starts the helium burning in the core. So they then basically like I said, the star moves off into the red giant stage. But of course, as we said, helium is a very, very friendly gas, and it loves to have mates. So it's quite happy to join with other atoms and of different types. We know it will join with oxygen because H2O gives us water, hydrogen and oxygen. But also it likes to join with carbon. And once it starts joining with carbon, you get what you call your sort of like hydrocarbons, your long chain atoms, which then go on to make more. Basically, they go on to make life. They're the starting blocks of life. So basically, that's all I wanted to say about hydrogen without getting too technical. That basically, we at the very beginning, we started off with 75% hydrogen, 24% helium, and 1% other little bits and bobs. So hydrogen really is the building blocks of everything that we see in the universe.
Right.
So,
Right.
so I thought I'd just start off with a quick one.
And there's just one interesting thing about hydrogen and helium and lithium. These are the lightest elements in the universe, as you know. And anything heavier than that, astronomers think obviously came along, manufactured in the hearts of stars, and then blown throughout space as supernova explosions. So anything heavier than hydrogen, helium, and lithium is called by astronomers a metal. So they talk about metal-rich and metal-poor stars, and it doesn't literally mean metal. It means anything heavier than hydrogen, helium, and lithium. But the interesting thing about those three elements, hydrogen, helium, and lithium, is that the Big Bang Theory predicted in what ratios they would be found in the universe. And one of the great successes of the Big Bang Theory was that when the observations were done, they are found in exactly the proportions in the universe predicted by Big Bang Theory. So this was another confirmation of Big Bang Theory before the discovery of the cosmic microwave background, which is the final clincher, if you like. But Big Bang Theory is so successful that it was able to predict the relative abundances of hydrogen, helium, and lithium in the universe, which was a hell of an achievement.
Yeah, yes, it's just one of those things. It's like I say, we started with so little after the Big Bang, and it's gone and through to stars, supernova, neutron star collisions, and things like that. We've ended up with all the elements that we
Yes,
see.
absolutely.
And without this process, we wouldn't exist. And it's just one of those thoughts that without hydrogen, and at the very beginning, that none of this would exist, and we wouldn't be able to. We wouldn't be sat here talking about it.
No, absolutely.
And it's just one of those weird coincidences that it's hydrogen, just one sort of like element that has started this all off and started us on our long journey.
Absolutely.
And long may it rain, as I say.
Yeah, absolutely. H is for Hyperion, which is a moon of Saturn, as you know. And it was discovered in 1848, believe it or not, by William Bond, his son George Bond, and another
Bond.
Not Brooke Bond, no.
Okay.
And another astronomer called William Lassell, who discovered it sort of independently of the Bonds in 1848, as I said. Now, the interesting thing about Hyperion is it's strange. It's a strange moon. Firstly, it has a chaotic tumbling movement through space. So it doesn't have a rotation, if you like. It has a tumble. And that rotation, if you like, that tumbling cannot be predicted because it's totally chaotic. It also has a really eccentric orbit around Saturn. But perhaps the most interesting thing about it is it has an unusually low density for a moon. It has a very low density. And because of this, it looks like a sponge. And if you look at the images that the Cassini spacecraft took of the moon Hyperion, it really does look very odd indeed. It looks porous, if you like. It's covered, absolutely covered, in small craters that are, there's no space between them. It's like the holes in a sponge. And at the bottom of each of those craters, there's a dark material. Of course, obviously, the question is, how did a moon get to look like a sponge? And what scientists believe is that the moon is of such low density that when something hits it, a rock from space, in something denser, it would carve out a big crater. But with something of low density, rather than excavate, it compacts. So because of the low density, the impact, or if you like, slams into the surface, compresses the material, but doesn't gouge out a huge crater. So Hyperion is pockmarked with small, tiny holes, if you like, giving it its sponge-like material. Because 40% of Hyperion is reckoned to be just empty space because of this. And the material that is thrown out when these holes are made doesn't return to the surface because the gravity is so low because of its low density. So all this material is constantly being lost to space. So 40% of it is empty space. And it allows those craters that have formed to remain pretty much unchanged over the eons for billions of years. Hyperion is composed mainly of water ice. There's very little rock. It's almost all ice. And we never had a good look at it until Cassini. And Cassini made two approaches to Hyperion. And the moon is 360 by 266 by 205 kilometers in size. So it's actually, it's not a tiny moon. It's quite a sizable moon, a few hundred kilometers across. But it is very odd that it's ended up like this. And in fact, it's the only moon that we know of that actually looks like this. And it was indeed the first moon ever to be discovered that wasn't round. So when the Bonds and Mr. Herschel discovered it in 1848, it was the first moon ever to be discovered that isn't spherical, if you like. And of course, at that time, they really couldn't get an image of it, but they could certainly see that it wasn't spherical. And they observed it over, months and months and established that, it definitely wasn't spherical. but they would have been absolutely amazed at the Cassini images of it, because it's a bizarre moon, the only one of its type in the solar system as far as we know. So there we are, and that's Saturn's moon Hyperion for you.
Right, okay then. If you don't mind, I will continue along this theme straight away.
No, go on.
And I am going to talk about Helios.
Helios, right.
The sun. Right?
Okay.
As we know now, we're going down the mythology route. And the reason I sort of smiled when you said Hyperion is that Helios, as we know, is the in Greek mythology is known as the sun. And his parents were Hyperion and Thea.
Ah, right. So there's a connection there.
There is a connection there. And he, basically, as they in the Greek mythology, the sun rides on a chariot, and it crosses during the day from one palace to another, and then disappears, and then he rises again in the morning. Well, as I said, his parents are Hyperion. His mother is Thea. Now, as we know, we have the Thea philosophy, where Thea was the impactor that hit the Earth and
created the moon.
And created the moon.
Yes.
By destroying by destroying the Earth and destroying itself and most of the Earth, it formed a rubble halo, and that's how the moon came about.
Yes.
That's the favorite. That's the theory at the moment. There's nothing better either. So there's some people thought it was a court that captured asteroid and things like that, but no. So yeah, so Thea was now his siblings were Selene, which is the moon.
Yes, absolutely.
And we had Eos.
Ah, right.
Now his grandmother was Gaia.
Good grief.
So we had Gaia, who is Mother Earth, who's the personification of Earth. And basically Gaia was one of the primordial beings. Out of chaos came 6 beings, and one of them was Gaia. And she created the Earth and everything around it. Now, she was fed up of being alone, so she created a partner. She made him. So basically, you would say, and she called it, basically his name was Uranus.
Ah.
And these names ringing a bell, are they?
Yeah, just a bit. Yeah.
And of course, so she made Uranus, who became her partner. So basically, she was. I hope people aren't squeamish and make these sort of things. So basically, she had relationships with her son because she made him. They had, as I said, they had quite a few children. I think it was 12 altogether. And which included Hyperion, Thea, because again, Thea, as I said, she was Hyperion's wife, but they were, in theory, brother and sister. But they were what were called the Titans, which were the pre-Greek gods, the ones we know, Zeus and things like that. So, and to actually know the story is quite in a way it's quite sad, because when like I said, Gaia actually rebelled against Uranus, and she got together with one of her sons. Again, you'll know this name, Kronos.
Oh yes.
Another moon. And they overthrew him. Now, what they did to him, you don't want to know.
Right, okay.
It wasn't very nice. But also, before all this happened, Uranus was looking, and Gaia were looking to say, well, who's going to take over the reins once we do move on, whatever they are, you know? And they were edging towards Hyperion and Thea taking over the reins. Now, Kronos didn't appreciate that. He wanted the power to himself, and he thought if Hyperion and Thea got all the power, he would be left out in the cold. So what he did is he kidnapped Hyperion, Hyperion and Eos, who was the youngest daughter, and she is Eos is Dawn. She is the personification of Dawn. And he drowned them.
Oh,
Selene,
nice.
upon hearing the bad news about Hyperion, who she loved dearly, threw herself off the highest tower, killing herself.
Right.
When Thea heard of this, she was totally distraught, and she went along the river. I can't remember the name of the river, but that's irrelevant. But she went along the banks of the river until she found Hyperion's body, because she loved him so much, and she was so distraught. But while she was there, she swooned, but she had a vision that Hyperion visited her and said, don't fret, because we will become famous, people will revere us, and we will be made immortal. And of course, so what she did is she just took up all the items like cymbals, drums, all the children's implements, toys that made noise, and she wandered around the land, banging up, making a hell of a din. People were and she became very bedraggled, very sort of like a trampish like, and she. Eventually, people became to sort of like revere her, and men swooned at her feet and things like that. And eventually, what happened is one night there was a very bad thunderstorm, and she totally disappeared. So the people believed that she was some sort of goddess and things like that. So what they did is they took the three children, and as I said, they made Helios the sun.
Yeah.
The personification of sun, Selene, the personification of the moon, and Eos, the dawn. So that's how we ended up with Helios as the sun.
Wow, that's amazing. Isn't that a lovely story?
Yeah,
you've got to love these old legends, haven't you? And the myths. I mean,
well, I do. When you look at the mythology, especially the Greek mythology, and as you pointed out last week, there's always when they the International Astronomical Union, astronomical, them, name things. There's always a theme, and as I said, you go through this, and then as I said, these Hyperion, Thea, and their children, all that, and Kronos were the Titans, and of course they end up fighting with Zeus. The Olympus gods, as they
the Titans were always clashing, as we know.
That's right, the Clash of the Titans. But Gaia, as I said, Gaia was originally the original being, the deity, who, like I said, she was one of the primordial gods that came out of chaos, because that was the Greeks.
Well, whatever else you want to say about the ancient Greeks, they were not lacking in imagination.
No, exactly. And they read these stories,
some beautifully detailed stories, and
but some of their morals were, let's put it this way, right from Gaia all the way down through, even with the Olympus gods, their morals were very lax. Let's put it that way.
Yeah, but I mean, that's the morals of their time. That's us judging them by our current morals, which I don't think you should really do.
So as I said, when you read it, you've got to sort of like open your mind and say, well, you know. But but that was it. It's just the fact that you mentioned Hyperion. And I thought, well, I've got a little tale about Helios, so let's put it in there. And it's all to do with Greek mythology.
Yeah, and that was so interesting. Thank you, that.
Yeah, and as I said, you'll find all these names in the heavens.
Yeah, so, absolutely.
That is Helios.
We're going to stay with ancient Greece. H is for Hipparchus. Now, Hipparchus is seen as the father of astronomy. He was an ancient Greek astronomer who lived between 190 and 120 BC. He was the first person to compile, or the first known catalogue of stars and the first map of the skies, in which he listed between 850 and 1,000 stars, organized by constellation. So he was really the first person to adopt a systematic approach to mapping the heavens. So the foundation of astronomy, if you like. He, about each star, he made a note of its position in the sky and its brightness, and he invented his own brightness scale, which ran from 1 to 6, where 1 was the brightest and 6 was the faintest. And he also invented or was thought to have invented, the astrolabe, which we talked about a few weeks ago. So he was a real pioneer in lots, not just astronomy, lots of different fields. For example, he's thought to be the first person who developed trigonometry. And do you remember those awful trigonometric tables that we had at school that didn't understand a thing about them? He's the first person thought to have invented those. And he needed to, because in his mapping of the skies and also other things that he was doing, he needed to investigate the field of spherical trigonometry, where you take trigonometry and apply it to a curved surface, basically. Because obviously, to the ancient Greeks, they thought the sky was a curved dome, so he had to do calculations based on spherical trigonometry. He may have been also the first person to develop a reliable method for predicting solar eclipses. And he did manage to compute the eccentricity of the orbits of the moon and sun quite successfully. And also, he discovered the Earth's precession, which is that thing over thousands of years where the Earth's axis wobbles, and therefore the pole star changes over thousands of years, because the Earth's axis describes a circle in the sky, so that the pole star is always changing. We've got Polaris as nearly the pole star at the moment. It's about half a degree away from the North Celestial Pole, which, for those who don't know, if you take a line through the Earth's atmosphere upwards, and point it at the sky, where it meets the sky is the North Celestial Pole. And luckily for us, we have the star Polaris at the North Celestial Pole, which means when I'm aligning my telescope, I align it with Polaris. And to be honest, the fact that it isn't exactly at the North Celestial Pole doesn't bother the navigation of the computer at all of my telescope. It seems to be fine. So he was among the first people to calculate how would the solar system work if the sun were at the center of it. And don't forget, at the time, the prevalent idea was that the Earth was at the center of the universe. Yeah. But he calculated how would the solar system look if we put the sun at the center of the solar system. And what he found was it actually worked. But in working out all these calculations, he inadvertently discovered that the orbits of the planets are not circular. They are slightly elliptical. And he rejected that work on the heliocentric system, putting the sun at the center of the solar system, simply because the prevalent belief at the time, which was pretty much immutable, was that everything in the sky is perfect, and therefore the orbits of the planets are perfectly circular. And once he discovered that they weren't, he assumed that the heliocentric model was in error, and that Earth is really the center of the solar system. So all of this work he did, predicting solar eclipses for the first time, the work with trigonometry and spherical trigonometry, and discovering the precession of the Earth. He was an amazing person, and is quite rightfully, I think, seen as the father of astronomy. So that's Hipparchus.
Yeah, because as you said about the circular motion, as he said, he didn't. Although he discovered that the orbits were elliptical, he didn't know that's what he had discovered.
No, he didn't.
And so what he had is he had the Earth already rotating around an imaginary center of rotation, yes, to give you the effect of, you know, moving around the suns and the orbits and things like that. So as you said, yes, he did scrap that idea. But also there was something here, well, because as I said, I've got exactly the same, and it's something to do with Schrödinger Schrodinger numbers.
Oh yeah.
And it's yeah, I won't go into it because it's very, very complicated. But he discovered these numbers, and it wasn't until um, until 1870, because of course, as you said, he was around millions, well, hundreds of years ago, 120 BC
Mm.
to 190, circa 190, and it wasn't until 1870 that Ernst Schroeder rediscovered these numbers, and it's a formulation.
Mm.
I don't understand it, so I'm not going to really go into
No,
it. 'Cause
don't worry. If you don't, I
it
won't
really,
either.
yeah.
So don't worry.
So it's very, very confusing. As you said, he was a very remarkable guy, and he had his fingers literally in so many different
Yeah, he did. He was amazing.
but again, we keep coming back to these old dudes, and they didn't have the equipment we have.
No, they just had their eyes basically,
They
and
just had their
very
eyes,
rudimentary measuring instruments.
and their sort of brains, and they were able to work out and deduce what was actually happening in the skies. And a lot of these things were only have been confirmed sort of like in the last sort of like 300 or 400 years. Because also one of his legacies was that he did ponder whether or not the so-called fixed stars were actually fixed, or whether or not they do move. And
Right.
he predicted that if these if these stars moved, then the constellations would change over time, which is correct. Because if you look at, say, like the Big Dipper or Ursa Major, what it looks like in 100,000 years BC to this day, and then what it's going to look like in 100,000 years
Yeah.
time, it's going to look completely different. So he was already saying that nothing is fixed in the skies. And it's called Proper Motion of Stars, which, if I remember right, is Edmund Halley. Was
Yes.
it him who
Yes, I
came
think
up with that?
yes.
One
Yes,
of
that rings
his,
a bell. Yes,
yeah,
it's
Edmund
Halley.
Halley.
Yes.
So yeah, that's just a little bit. Yeah, so very intriguing guy. Very, very
But you think
intriguing.
about it, if he had been born later, making those discoveries and those measurements, it would have brought him into contact with the Catholic Church.
Yeah, yeah,
And
of course, yeah.
he would have gone the way probably of Giordani Bruni, who was burned at the stake by the Catholics for basically saying that there were other planets in the universe, and that we're not unique, amongst other things, amongst other heresies.
I mean,
So
Galilei, wasn't he? He was
Galileo, who
so
escaped luckily with only house arrest instead of execution.
exactly, yeah. But
it just makes you realize that once the Catholic Church dominated society,
yeah,
then it was a regression of knowledge and a persecution of knowledge. Anything that disagreed with church dogma, people were murdered over. So
exactly,
people, we've talked a lot about the ancient Greeks on this program, and very much of their work would have been banned by the church, and they would have, might well have lost their lives.
Heretical,
because
heretical.
There was no freedom on intellectual expression in ancient Greek civilization.
Yeah.
It took the Catholic Church to kill freedom of expression, freedom of belief, which is ironic, really, considering it's a church. But so there we are. So that's very interesting about Hipparchus. But all astronomers are indebted to him for the things that he did. But I think more than anything, his approach to things, his methodical, analytical way of examining the universe, not to attribute everything to Greek gods, but to try and work things out in a systematic way, and developing systems of measurement using things like trigonometry, which hadn't been around before, that enabled him to create his catalogue and his maps. Fascinating guy, absolutely fascinating.
And as you said, his magnitude scale.
Yes, his magnitude scale, which was the first time I think that anybody had actually formalized the brightnesses of stars in a scale.
I mean, it didn't. There was only sort of like, I think about what 7 or 8 numbers, because he didn't have the telescope, or
No,
probably,
absolutely. So I mean, the limiting magnitude of that system was his naked eye, basically.
Exactly, yeah.
But at least he thought to, classify stars by their brightness, which I don't think, I may be wrong, but I don't think anybody done that in quite that way before.
No, I don't think it was.
Of course, it was a linear scale from 1 to 6. And so a star of magnitude 3 in his system was 3 times fainter than a star of magnitude 1. So it was a linear scale. Of course, these days we use a modern magnitude system where the relationship between the magnitudes is a bit more complicated, because each successive magnitude is 2.5 times brighter or fainter, depending which way you're going, than the preceding one. So, for example, if you have a star of magnitude 1, a star of magnitude 2 is 2.5 times fainter than magnitude 1. And a star of magnitude 0 is 2.5 times brighter than magnitude 1, and so on and so forth, which I've always found extremely confusing. I don't understand why we just can't use a linear scale.
Yeah, because it's excuse me, because what we've got to remind our listeners is that it works backwards. You would have thought the higher the number, the brighter it is, but it's not.
Right, it's not. It's the lower.
And then, of course, then you've got the really bright stars that go into the minus side of it as well. So,
and if you take something like the sun, which is magnitude minus 25, so you start at 0, you think, well, minus 25, but then -1 is 2.5 times brighter than that. -2 is 2.5 times brighter than that. -3 is 2.5 times, and so on. And you get to -25. Now, for the life of me, I just find that confusing, and I always have, because it doesn't give you a mental image of how bright that actually is. If it were a linear scale, it would be a lot easier, I think. It would be a lot easier, because you could then say that a magnitude -25 object like the sun is twice the brightness of a -12.5 times object. So it would be a lot easier. You could work things out a lot easier than that. I have no idea why that scale was
no adopted. Exactly. There seems to be no.
We can discuss that when we come to M on this program. To investigate that.
But as you said, Jess, it's because when I did my university course last year, when we did have some nice weather, you use the magnitude scale, and as you said, it was this multiplication thing and all that going on. And I found the easiest way to go out was write down the magnitudes of some constellations and just go outside and have a look. Get the gist of what's going on, because as you said, numbers really don't mean a lot. It doesn't take.
No, they don't. They don't. They
don't. The brightness is, and it gives you, then what people are talking about and get a gist of it.
And really, it's only useful for local stars. Because when professional astronomers look millions of light years out into the universe, the magnitude system becomes a bit irrelevant, really.
Because you're talking about time as well, and so
So
you're looking back on. Okay, so what you're actually seeing, isn't it?
Yeah, that's right. So that was Hipparchus.
H is for Herschel.
Funny enough. Which particular Herschel?
The one who was with the Russell guy who made that diagram. No, I'm talking about Caroline.
I wondered if it might be Caroline. Well, this is good, because everybody always talks about William. Let's hear about Caroline.
Exactly. Caroline. We haven't touched on many women. So I thought, right, we won't talk about Mr. Herschel. We'll talk about Caroline. Okay. And in fact, there was 3 Mr. Herschels. But Caroline had a very interesting life on her own. And I'll just give you a quick run through of her life, an abridged version. She lived 1750 to 1848. Caroline Herschel began her life in astronomy, supporting the work of her amateur astronomer brother, William. She was working with him when he discovered Uranus. Now, we know that's not correct. She wasn't there.
She wasn't there. She wasn't out of the shops.
Yeah, she was disco-ing. She was DISCO. And she became the world's first professional woman astronomer. Her salary provided by King George III of Great Britain.
Right.
The catalogue of nebulae she produced brought her the British Royal Astronomy Society's 1828 gold medal,
Right.
their first awarded to a woman. So she's got lots of firsts to her name, not just, all of the stuff that she did with her brother.
Quite an achievement then.
Exactly. She personally discovered 5 comets and rediscovered comic ink.
Oh, Comet Ink, yeah.
Ink, yeah. Working as a team, William and Caroline Herschel increased the number of known nebulae from about 100 to 2,500. So they were busy people. And this was all done in Bath. Well, most of it was done in Bath. Let's sort of say 90% of it.
Right.
If you talk to Simon, they did it all there.
Of course.
Caroline Lucretia Herschel was born in Germany, in the German town of Hanover in March 16th, 1750, the 8th child of Isaac Herschel and Anna Ilse Moritzen. Isaac was a musician, while Anna was illiterate and vehemently opposed to the education of girls, believing they should work only at home. Ooh, very negative. And Anna objected to Isaac's attempt to educate his daughters, even opposing violin lessons. So she didn't even want them playing music.
Right.
Caroline, she had a bit of a fraught life. Caroline suffered smallpox at the age 3, leaving her face marked.
Oh, really?
Sorry?
Sorry.
Yeah,
I didn't know that.
I didn't know that.
No.
She also suffered typhus, stunting her growth. This is why she was so short.
Right.
At the age 11. Her father and mother believed it would be difficult for Caroline to find a husband. Her mother decided Caroline would become the family's domestic servant.
Right.
Caroline's brother William moved to the English city of Bath, where he taught music, performed in concerts, and was a church organist. William wanted his younger sister, Caroline, to have a better life than she could as their mother's servant. He proposed to the family that Caroline should come and live with him in Bath, train to be a singer, and give concerts with him.
Right.
In August 1772, William returned to Hanover and took Caroline with him to Bath. He agreed to pay his mother for a servant to replace Caroline, who had been doing most of the household chores. Life in Bath was not easy for Caroline. She was poorly educated and spoke little English. She did housework for William, who taught her English and mathematics. Breakfast was always taken with a math lesson. William gave Caroline singing lessons 2 or 3 times a day. She took dancing lessons, and in 1777, aged 27, she was a notable soprano and had sung the lead works such as Handel's Messiah. However, William's passion for music was decreasing and his passion for astronomy was increasing. He felt driven to understand the heavens better than anyone before. He desperately wanted to see other objects so faint that nobody had seen them before. To achieve his goals, he needed the greatest telescopes in the world. The only way to get them was to build them himself. A remarkable endeavor for an amateur to consider, never mind tackle. William became so obsessed with his goals that, in addition to help him grind mirrors and lenses, Caroline often had to prepare food and feed it into his mouth while he worked, spoon-fed.
Oh, really?
Yeah. In March 1781, William discovered Uranus. Since prehistoric times, our ancestors had known Mercury, Venus, Mars, Jupiter, and Saturn. Herschel's discovery of a new planet was a singular moment in the history of science. If a planet had remained unrecognized for so long, what else might be out there? After all, Uranus was actually visible to the naked eye.
Yeah.
British scientists petitioned the king, asking that Herschel be paid a government pension to allow him to give up music and devote his life to the construction of his magnificent telescopes, offering the possibility of making further stunning discoveries. The king agreed, and William became a full-time astronomer. He assumed Caroline would be happy to give up her musical career to act as its assistant. Caroline was far from happy. She had escaped drudgery in Hanover to become a singer, praised and loved by audiences. She now had to abandon her singing. In August 1782, aged 32, she moved with William from Bath to Datchet, near Windsor Castle, closer to the king. Her first months as a full-time astronomer were miserable and lonely. She described her thoughts as, "I was to be trained for an assistant astronomer, and by way of encouragement, a telescope adapted for sweeping the night skies was given to me.
Okay.
I was to sweep for comets, but it was not till the last 2 months of the same year before I felt the least encouragement for spending the starlight nights on a grass plot covered by dew or hoarfrost without a human being near enough to be within call."
Ah.
So she wasn't that happy.
No.
The things were looking up. Astronomy joke. By the end of the following year, Caroline had discovered 4 comets, and she felt much happier. To be the first human to see these remarkable objects inspired her. During her career, Caroline discovered and co-discovered 8 comets, 14 nebulae, including the 1783, the Andromeda Nebula's companion Messier 110, also known as NGC 205.
Right.
Excuse me. In 1788, Caroline discovered the periodic comet 35P Herschel Ridgelet. This comet will return in 2092. In 1795, Caroline rediscovered the remarkable comet Encke. The comet on a 3.3-year orbit of the Sun. The comet was first discovered by Pierre Michelin in 1786.
Doesn't Comet Ink give us one of our annual meteor showers?
It probably does, but I couldn't tell you which one.
No, I can't remember. I'm sure
there's been
one
a
of
new
them meteor
survey
showers.
just yeah, there's
It's a
been
very short period comet, isn't it?
yeah.
Yeah.
There's a new survey that's been done that's actually been looking for lost meteor showers.
Oh yes.
And some of these showers that were some of these meteorites that we or meteors, meteoroids that we see in the night sky, which we call random, turn out that some of them aren't, and they actually are part of ancient showers, which they think could indicate that there are ancient comets that are possibly over thousands of years are doing their orbits, so they could come back at any time because we don't know where they are. But
No.
these so-called meteoroids all sit in the same spaces, so they've discovered, I think it's about 6 new showers that go throughout the year.
Wow.
So what else have we got about? Yes, so in October 1783, William finished building a superb instrument, an 18-inch, which is 460 millimeter reflecting telescope with 20-foot focal length. Oh, that's a big one.
Oh, big.
He and Caroline became one of the most formidable teams in astronomy has ever known. Night after night, William would systematically observe different regions of the sky, calling out sightings, declinations, and right ascensions of nebulae. Caroline recorded the observations, making the necessary calculations to standardize them for factors such as time. Then compiled the data ready for publication in journals. In 20 years of ceaseless exertion, William and Caroline increased the number of known nebula to, as I said before, about 2,500 from 100. In 1787, at the age of 37, Caroline began receiving a pension from King George for her work. She became the world's first professional woman astronomer. The age of 75 and in retirement, Caroline learned that William's son, John Herschel, intended making an updated catalogue of nebulae. To
Right.
make life easier for her nephew, she undertook a huge reconstruction of the existing catalogue so that no nebula were listed by position rather than class.
Right.
As I said, her work got her the gold medal in 1828 from the British Royal Astronomy. Caroline was devoted to her brother, who had rescued her from drudgery and poverty. In 1788, William married Mary Pitt. Now, things went a bit awry then, if I remember
They
right.
did, yeah, that's right. There was
A
a bit of
local
friction there,
widow.
wasn't there?
Yeah, a local widow, which seemed to have made Caroline deeply unhappy. As time passed, however, relations between the two women improved. Caroline doted on John Herschel, the sole child from the marriage. We're nearly at the end. William died in 1822. He left Caroline an annual income in his will, enough for her to live very comfortably, believing she would soon die herself. That was nice.
Oh, nice.
Age 72, she sought the familiarity of her childhood surroundings in Hanover and returned there to live with her brother Dietrich and his family. In fact, she lived for many more years. At age 75, her devotion to her nephew John Herschel pushed her into a frenzy of work to produce a formulated catalogue. Well, we've already discussed that.
Yeah. Dietrich
on-
had quite an interesting story as well, didn't he?
I don't know Dietrich, I must admit.
Yeah, I think he was a musician as well. He's not often mentioned alongside Caroline and William because they weren't much brighter lights, if you like. But I seem to remember reading something about Dietrich. But anyway, I'm sure listeners can check up on that. Look up Dietrich Herschel. I'm sure he was a musician. I think he was an organist, if I remember rightly. I may have just made that up in my own head, of course. But
they were a musical family, like I said, because
they were a very musical family, yes. And if anybody would like to listen to Herschel's music, you can find it on Spotify easily enough. And his music is marvelous. It's very English, very pastoral, and I really like it. So there we are.
Just the last bit.
Yep.
On a visit to her when she was 82 years old, John noted, "She runs about the town with me and skips up her 2 flights of stairs as wonderfully fresh, at least as some folks I could name who are not a fourth of her age. In the morning till 11 or 12 she is dull and weary, but as the day advances she gains life and is quite fresh and funny. At 10 or 11 p.m., so she was a nighttime girl.
Yeah.
At 10 or 11 p.m., and sings old rhymes, nay, even dances to the great delight of all who see her." And that was John Herschel.
That must have been the gin.
Yeah, exactly. Yeah, probably knew Kath.
It's probably Kath. Yeah.
In 1846, the great naturalist Alexander von Humboldt brought the 95-year-old Caroline a large gold medal from the King of Prussia, in recognition of valuable services rendered to astronomy by you as the fellow worker of your immortal brother, Sir William Herschel. Caroline Herschel died peacefully, aged 97, on January the 9th, 1848, in her home, Hanover. I would tell you where she's buried, but I couldn't pronounce the name of the place.
Oh, don't worry. Somewhere in Germany, I would guess.
Well, it's Garten Geminde. I don't know, Garten Geminde, in Hanover. It's in a churchyard.
So she actually lived a lot longer than William thought she would. So
yes.
I wonder if his bursary that he bequeathed to her lasted that long.
That's exactly, because he thought she was going to pop her clogs not long after him. But
that's right.
Interesting.
Her,
I mean,
Thank you very much for that, Daz. So it's it was so indicative of the time that women were expected to do all the drudgery and the menial jobs, and
Exactly, yes. Her
you
mother
know,
was very
men who had all the glory and the chance to advance themselves, whereas women were subjugated. There's no other word for it. But Caroline, quite rightly, has gone down in history for not just being Herschel's sister, but for doing valuable astronomical work herself.
exactly, yeah.
And which was not common at the time at all. If you think of any other women astronomers you know from that period, I can't think of any, to be quite honest.
Yeah, I mean, there's probably some there, but of course, I mean, these are German people, so maybe there was just but I was just going to say maybe there was a different way of life over there. But then thinking about what her mother wanted for her,
Exactly.
basically to be a housemaid, then obviously it wasn't, because, of course, we know later on, and as things went on, women could only they weren't allowed to produce scientific papers. That had to be done through their husbands. So their husbands got all the glory. They weren't also allowed to correspond with people of any note as well. So everything had to be done through the husband, and they were all pushed into the background.
And one thing that women, well, I'm not saying they weren't allowed to do it, but it was highly discouraged, was to use telescopes in professional observatories. You know, that was the province of men. Women weren't welcome in observatories at all. You know, it's just disgrace for the whole thing. So having mentioned Caroline Herschel, coincidentally, we move on to another female astronomer now.
Excellent.
Henrietta Swan Leavitt. And she has a rightful place in history, as does Caroline. She lived from 1868 to 1921. She was an American astronomer. She graduated from Radcliffe College in the States, and she went to Harvard, where she studied a broad curriculum that included Latin, classical Greek, fine arts, philosophy, analytic geometry, and calculus. So she was very much of a mathematical bent, as it were, but she did do, classical Greek and fine arts as well. But at that point, she wasn't into astronomy. She didn't do an actual astronomy course until her fourth year of study at college. And she got an A- for that. So she obviously had some ability in it.
Yeah.
And she was taken on at the Harvard College Observatory by its director, Edward Charles Pickering, who we might talk about when we get to P, because he's quite an interesting guy. And she was taken on as a sort of a human computer, which was the province of women in those days. Women were taken on to measure and calculate and catalogue the things like the brightness of stars. Now, the observatory had a huge collection of photographic plates. And in those days, of course, photography was done on glass plates. So that there was a huge collection of glass plates at the observatory. And Henrietta Leavitt was taken on to catalogue these and to measure the brightness of the stars in the plates. So it was painstaking work, repetitive, painstaking, not at all exciting work. But women were thought to be very good at this type of work because, whether it's true or not, women were thought to be very good at image recognition and measuring the brightness of things. But they were, very much taken on as human computers. And she wasn't allowed to operate the telescope, of course. She couldn't take her own photographs. So she was reliant solely on the work of the male astronomers. But in 1893, she did obtain credits towards a graduate degree in astronomy, but she never completed it. In 1898, she joined the Harvard staff as their first curator of astronomical photographs. And she traveled in Europe. She completed a stint as an art assistant at Belvoir College in Wisconsin. And at that time, she caught a disease that caused her gradually to lose her hearing, which was obviously, not very pleasant. So we come to her major discovery in astronomy, and this is what she is known for. She discovered the period luminosity relationship in Cepheid variable stars, which we've talked about before on this program.
Yeah.
So let me just recap for anybody out there who doesn't know. So there's a type of star called a Cepheid variable that pulsates. And there are lots of different types of Cepheid variables that pulsate for different reasons. But the basic idea that applies to them all is that they're pulsating stars. They get dimmer, and then they get brighter again, and then they get dimmer again. And the length of those cycles depends directly on the brightness of the star. So a Cepheid variable of a particular brightness will pulsate with a particular period. This was significant for astronomy, because if you know the brightness, if you know the pulsation period, you can work out the brightness of the star. And if you can work out the brightness of the star, how bright it appears in the sky, you can actually work out how far away it is. And because of this, Cepheid variables became known as one of astronomy's so-called standard candles, because they could give you the measurement of how far stars are away out to about a distance of 20 million light years. Before Henrietta Leavitt discovered this relationship between the period of the Cepheid variable, how long it takes to pulsate, and its brightness, astronomers had to use things like parallax and triangulation to measure the distance of stars, neither of which is an incredibly accurate method. So this was Leavitt's major contribution to astronomy. Without that work, Edwin Hubble could not have completed his work, where he managed to identify Cepheid variables in the Andromeda galaxy, M31, and calculate how far away they were. And thus, astronomers finally realized that those smudges of light in their telescopes were galaxies in their own right, and not nebulae within our own galaxy, which had been thought up until then. Henrietta Leavitt deserves her place in history for figuring out that there was a relationship between the brightness of a Cepheid variable and its variability, how long it cycles over in terms of getting brighter and getting fainter again. And there you are, and an amazing lady, absolutely amazing lady. But of course, a product of the time,
Exactly.
very much overshadowed by the work of male astronomers at the time.
Yeah.
And when Hubble discovered the distance to Andromeda, very little was said at the time about the fact that he had managed to do those calculations based on the work of Henrietta Swan Leavitt. She was eclipsed, if you like, by the famous male astronomers of the time.
Yeah.
So there you are.
It's an like you said, it's a sign of the times, because the Harvard computers, there's several of them whose names have come forward as being the instigators of theories, of observations that were made. But as I said with when we were talking about Caroline, it was frowned upon for women to
do anything, basically.
To do anything, yeah. They weren't allowed to produce
menial drudgery.
Yeah, they had to do it through their supervisors and things like that, which were all men, so they took all the glory.
And as we know, I mean, even in the 1920s, in many colleges and universities in the United States, women were still not allowed to get degrees.
No, that's exactly, yeah. They were allowed to.
And even up to the 1950s, there were still a few colleges that you could not do a degree course if you were female.
Exactly. I can't remember the name of the lady, but it was a lady who actually formed her own university, which they did start issuing diplomas and things like that for women.
Oh, really?
Then, of course, it all, as I said, it's very, I mean, first of all, they deigned to let women attend university, but as you said, they weren't allowed to gain qualifications. Then eventually, as I said, this, I can't remember the name of the lady, who set up her own university and her own courses, and they were able to gain qualifications that were recognized. And eventually, I mean, even when I was talking about Dame Jocelyn Burnell, we're talking
Yes,
about
we talked about this, didn't we? With
it
Dame Jocelyn,
was.
yes.
I mean, the times were so sexist,
Mm.
and it was her supervisor and his supervisor that got all the glory for her
For
finding the
discovering
first four
pulsars, yeah.
pulsars. Yeah.
Yeah.
But well, we'd like to think things are changing.
Hmm.
They're on the up.
Yes, yes. It's
So
still not easy
no.
in some fields of science, certainly for women to gain the recognition and the opportunities that they should.
Exactly. It's just a total shame that all these people were kept in the shadows. What they could have done if they were given
Exactly.
the same as the men, it would have been amazing.
Yeah.
So yeah, Henrietta Leavitt, because
It's 11.
yeah, because it's because it isn't part of this Cepheid variables part of the so what they call it, the cosmic ladder.
Yes, absolutely.
Yeah, where you build up
Yeah.
to get your distances and all
Yeah,
that.
the cosmic distance scale. Yeah.
Yeah, it was an amazing discovery.
Amazing discovery.
Yes, but wasn't it she did the main study on, was it on the Small Magellanic Cloud, if I remember rightly?
Yes, I believe so.
Yeah, so that's where she studied the variables and all that, and then she realized that they all had the same sort of life cycle, and so yeah, very, very clever lady, very clever lady.
Yeah, there we are.
H is for, and I'd like to know if you've ever heard of this, huge, large quasar group.
It's funny you should say that because no, I've never heard of them.
No, and it's not just huge; it's large as well.
How can it be? How can it be huge and large?
It's a larger huge, isn't it? It's a huge large.
Okay,
so,
it's a huge large. All right.
Yeah, it's a huge large.
Okay.
Yeah,
so what is this all about?
It sounds like a McDonald's portion, isn't it?
Yeah, that's right.
Quasar, no, supersize me.
Yeah.
So, well, basically, it ties in. Can you remember you were talking about the Great Void?
Ah, yes. In low 80s, yes.
Last week, yeah, the Great Void. Well, this sort of links into, and where you said it was sort of like it's considered to be was it me you said, or yourself, a bruise from another universe?
Possibly, yes. That's one idea, yeah.
Well, this sort of like comes into the same category. I'll read what it actually says, and then you can tell me what you think. It basically it's all to do with the CMB, the cosmic microwave background. Our color maps of the cosmic microwave background are littered with red and blue speckles representing the slightly hotter and cooler regions of the infant universe. Well, of course, these variations are really minuscule.
Oh, they're millions of a degree.
Yeah,
they're tiny,
but they do make a lot of difference. In 2004, the WMAP, that's WMAP, which I can't remember what it stands for, saw one cold spot much larger than the others. Then the European Space Agency's Planck satellite discovered it too. If a supervoid sits in the same direction, then cosmic microwave background photons originating from beyond the supervoid, so the other side of it, would have to pass through it. Thanks to the accelerating expansion of the universe, the photons emerging from this barren area would find that matter was less densely packed than when it went in, leading to a drop in the gravitational potential they experienced and consequently their energy effectively cooling them down.
Right.
The supervoid itself isn't the half of it. As far back as 2012, a team led by Roger Clowes at the University of Central Lancashire, UK, claimed to have found an enormous structure strung out over 4 billion light years, more than twice the size of the supervoid. This time it wasn't an empty patch of space, but a crowded one. Known as the Huge Large Quasar Group, it contains 73 quasars.
Wow.
the bright active central regions of some galaxies, and that's what quasars are. They're overactive black holes that sit in the middle of galaxies, and they are throwing out huge amounts of energy because they're just feeding and feeding and feeding.
And we should point out as well, these are young galaxies, because they are billions of light years away. They're towards the edge of the observable universe. So we're looking at hyperactive galaxies radiating copious amounts of energy from humongous black holes when they were young. So it's thought that most, if not all, galaxies go through a quasar stage in their youth. That is to say, spiral galaxies. But, obviously, elliptical galaxies don't, because they're the results of mergers of spiral galaxies. But it's thought that all spiral galaxies go through this stage where the black hole at the center is pumping out so much energy that the quasars are incredibly bright. They can be seen literally across the universe.
Yeah.
And they have this black hole engine at their hearts, consuming vast quantities of gas. And the gas gets heated up to millions upon millions of degrees, radiates X-rays and visible light and ultraviolet right across the spectrum, and we can see them from billions of light years away. Anyway, sorry, proceed.
Yeah. No, that's fine, because I
clarify that.
As I was going to say, these quasars are so far away, so that we see them when they're really young, and but they're so far away, but they can be seen because of these really energetic black holes. So where was I? 73 quasars. Astronomers have known since the early 1980s that quasars tend to huddle together. They, don't like to be lonely.
No.
But never before had a grouping been found on such a large scale. Then in 2015, a team of Hungarian astronomers uncovered a colossal group of gamma ray bursts, GRBs, highly energetic short-lived flashes of energy erupting from distant galaxies. These GRBs appear to form a ring, a massive 5.6 billion light years across, 6% of the size of the visible universe, which is massive.
That's huge.
Massive. Such apparent violations of the cosmic principle make astronomers deeply uncomfortable. They may turn out to be mistakes. For example, one study from 2013 calculates that there is a fairly high probability of seeing an apparent structure within what is really a random distribution of quasars, although Clow's group disputed that conclusion.
Right.
Reynard Dick, a theoretical physicist from the University of Saskatchewan, Canada, believes that attempts to brush these cosmic megastructures aside are misguided. He says they should be embraced as our best bet of keeping the cosmological principle alive. All we have to do is accept that they don't actually exist. Instead, they are the first evidence of other dimensions intruding into our own, leaving 30 footprints behind on our otherwise smooth and homogeneous cosmic background, microwave background.
Amazing.
So that's what this megastructure was. But as I said, it links to the evidence towards possible other dimensions, universes.
And just to clarify the cosmological principle basically says that the universe looks the same in all directions.
Yeah.
And that because of this, if you can't really have any structure in the universe that is more than about 3 million light years across, because that violates the principle, that you've got a special case, if you like. But astronomers really believe that the universe should look the same in all directions, no matter where you are.
Yeah, no matter which way you look. Yeah.
Exactly. And this would appear to violate that. So, thank you for that, Daz. Really interesting. There are lots of things with the cosmic microwave background that, are just not really explained. It's not what astronomers thought it was going to be, that there are these gaps in it, holes, if you like. And this evidence of massive structures that really shouldn't be in our universe and may be evidence of other universes in the multiverse, if you like. The idea that there are lots of an infinite number of universes, and one of them may have butted against our own, and this is the This is the if you've got a ring of objects, it could be evidence of that. Time will tell, as they say. And speaking of time, it's caught up with us again, Daz, I'm afraid. So that interesting week, Daz. I think we had lots to choose from with H.
Yeah, and I've got loads left here.
Yeah, I've got quite a few left. Well, save them for next time. Next time we go through the alphabet, because as you may have heard, listeners, we decided that when we get to Z with the amazing astronomical alphabet, we're going to start again at A, because there's just a huge amount of stuff that we could talk about. So thank you so much for listening. Have a fantastic week. We'll be back next week with the incredibly previously unattained heights of the letter I, and so I've got a feeling I might be a bit of a tough one, but we will see. So from Daz and myself, thank you so much for listening, as I said, and we'll talk to you again next week.
Yeah, stay safe, everyone.
And I hope you've enjoyed the music of Hawkwind that we've played through this programme. And I'd like to dedicate all of the songs that I've played today to my oldest friend James, who, like me, started his musical journey with Hawkwind back in the long hot summer of 1972, when we both bought the Silver Machine single, and I remember being a bit peeved with the record shop that I got the plain one and he got the one in the picture sleeve. However, long time ago now. Thanks, Hawkwind, for all the decades of fantastic music. Keep on rocking, as they say. And I think we've got time to play a little bit more music from them before the end of the programme. So until we meet again on the amazing astronomical alphabet, this is Andy Briggs. If you want to email me to discuss anything on the programme, I am andy@astroradio.earth, and it's always a pleasure to hear from you. Until next week, stay safe. Bye-bye.